Okay, last time what we did is we did the rat problem in the math department at some university outside of Alabama, I believe. Is that right? I think that's it. We got our growth rate for the rats is the number of rats at any time t is 250 times 3 to the t over 1.3. And we answered a few questions. Now, there's nothing really wrong with this equation. It's fine. But scientists and mathematicians do not like to use base 3 or base 2 or base 5 or base 10. What mathematicians and scientists like to do, and they like to use base e. And there's a lot of reasons why they like to do that here. So it's e to some constant times t. The constant here is 3 to 1 over 1.3 times t, and there's some constant there, which we're going to hope to find and change to base e. Remember that e is a transcendental number. It is a non-repeating decimal, but we usually round it off to 2.72. So it's really not too much different than 3, but it is different. And what scientists and mathematicians like is that later on you'll learn when you take the derivative, it's very easy to handle in calculus. And also it's consistent. If every exponential is in e, then you can compare them. So they like the consistency, they like how easy it is later on in higher mathematics and to use for other things, especially to find the rates of change and things. So we're going to have to put it in, we're going to take this 3 to the t over 1.3, we're going to change it to e to the kt, but we've got to find out what k is. So what we do is we go e to the kt equals 3t over 1.3. Okay, and I want to find k. It looks like I have two variables there, but you'll see what will happen. It'll come out in the wash. And of course, this is an exponential equation. I want to solve for k. So I take the log of both sides. The log of e to the kt does equal the log of 3t over 1.3. Now, of course, the log of e to anything is anything. These cancel each other out because they're inverses of each other, and we get kt here. This equals, well, what does it equal? I can bring this out front. I can use one of the exponent law of logarithms to bring that out, and I'll have t over 1.3 times the log of 3 times the log of 3. Now, I can multiply both sides of this by 1 over t, and this t cancels out. And I can bring this up on top, and I can say that k equals the log of 3 over 1.3. And if I pop that in my calculator, can you get this down here well enough? So it comes out to 8451. 0.8451, that's what k equals, okay? So I can just go ahead and say, okay, well, I'll just erase this and go 0.8451. And if I did the questions that we did in the last lecture with 0.841 e to the 0.8451 t, I'd get almost exactly the same answers. We did have to round off a little bit, so you won't get exactly the same answer, but you'll get almost exactly the same answers. And using this e to the 0.8451 t times 250. And in the next lecture, what I want to do is I want to say, why don't we start out with e to the kt and see if we can solve that rat problem using that exponential. And that's what we'll do next time.